Let's talk about more complex things, because quite often you don't need just individual numbers. Sometimes you will have to operate, for example, on an array of numbers. How Python represents these arrays? There are two main concepts. One is called list and the other is called dictionary. And from perspective of a user who knows what array is, both are in principle arrays. The only difference is their underlying structure. There are also tuples and sets. The tuples are described later and sets are not used frequently, so are outside of the scope of this course. The lists are sequential memory blocks that contain some kind of variable or reference to a variable. So in case of an integer number list, for example, my list equal to 1, 23, 4, 5, 6, 7 is a list that contains elements. Let's type it here. Spaces are not necessary, but are there for eye candy. And if we take this variable, we can see that it actually is representing something that looks similar to what we have assigned to it. So the square brackets indicate that we are creating a list. Another way to create a list is by passing some iterator to a list function. For example, we can pass nothing, and it will create an empty list. Or we can pass range function that generates numerical sequences in Python. And my list now contains 0, 1, and 2. Now, accessing individual elements of that array, or list in this case, can be done in a similar way as in many C-like programming languages, with square brackets after the name of the variable and index inside. So 0 returns us 1, 1 returns us 23, and so on. The elements in lists are sequentially numbered from 0 to the number of elements minus 1. And if you try to access outside of the list, you will get an error. One key difference between list in Python and arrays in many different programming languages, like C, is that list in Python is not limited to containing only single data type. It can contain a mixture of integers, floating points, and strings. For example, let's create another list, name it mylist2, with the following contents. As you can see, if we print its contents out, it can correctly preserve all the different data types that we have here. This allows us some flexibility in what type of information we can store in lists. On the other hand, the language doesn't guarantee us that a list will have strictly the same data type. And we need to check for that separately. The alternative paradigm to lists is called dictionary. So while lists are basically sequential entities, and if you want multiple dimensions inside, then you just nest lists inside lists, and that works fine. We can define dictionary in two ways. The first one is by using dict constructor, into which we can pass different key value pairs, as you can see here. So in this case, they are separated by comma, and each key is indicated by the string on the left of the equal sign, and the value is on the right of the equal sign for each pair. When we look into this representation, then we can see that keys are now in single quotes to indicate that those are strings, and they are located on the left side of the column, and the values are indicated on the right side of the column. And all values have preserved their data types. So these keys here in dictionary constructor, they have been turned into strings because they are strings essentially. For this constructor, there is no other way. You cannot use any other key type in this constructor. However, we can also declare dictionary by just copy pasting this definition. Let's name it mydict2 and type it here. And as you can see, it created exactly the same dictionary. With this syntax, you can have keys that are not strings. For example, we can have a key that is an integer number 5, and we can have a key that is a floating point number 7.8. And this works just fine. The dictionary can take any type in Python for which Python knows how to calculate what is called hash. There is a built-in function inside Python, hash, and this function generates some repeatable value for every input value. And as you can see, the values for integers are just the integers themselves, and the value, for example, for a string is some sequence of numbers. And everything for which you can generate such hash can be used as a key. Once again, these pairs, these groups, are called key-value pairs, for that they have a key. This indicates the location in dictionary where this value is stored, and the value, what is stored at that location. The value of dictionary can be anything. It can be integer, it can be floating point, it can be string, it can be list, it can be another dictionary. So you can have multiple level of nested structures inside any dictionary. Okay, now let's try accessing some values from dictionary. With the same syntax as with lists, with square brackets and key inside of the square bracket, we can access, or at least attempt to access, some value. For example, for mydict2, key 5 is declared and its value is 1, so we get 1 as return. However, if we will try to access mydict5 from mydict, then the value is not defined because there is no such key as 5. And this is the first key difference. You can see that lists return index error because this is called index value and it is always integer. And then here dictionary returns key error, and key can be an integer, but it can also be something else. On the other hand, even if the key doesn't exist in a dictionary, we can assign some new value to that key, and it will be preserved in the same original dictionary. So as you can see, we now have new key 5 with value new value. Values from lists and dictionaries can just as well be part of equations. So we can do, for example, this way, and we can use plus operator on strings to add another part of string to our existing string. And the result would be new value underscore exclamation mark. From the point of organization, dictionary is what's called in programming hash map, because it maps values by their hashes. And you can find more information about that in mathematics textbook or on Wikipedia. This type of storage that utilizes hashes instead of actual key values removes reliability on sequential storage that list has, and also allows dictionaries to be very quick in terms of accessing of arbitrary object and addition of new ones, because the objects don't have to be located, and they are actually not located sequentially in the memory. It doesn't really matter how large is your dictionary or what is your key. It can be any number or string, it will be still reduced to this hash, and the access time will essentially be the same. You can access values from the dictionary with the same speed. But there are two drawbacks with dictionaries. One drawback is that dictionaries are not really easy indexable. So for list, you can just iterate numbers from 0 to the size of list, and you are guaranteed to get some number at every point. With dictionary, the presence of sequential keys is not guaranteed, and that would be actually counterproductive to have something like that. So if you want to have index for a dictionary, you will have to build that one manually. Luckily, you can actually access and iterate over keys of dictionary. If you take list of any dictionary, then as a result, you will get a list of keys. So you can use this list with these values to access keys from the dictionary and their values. We will do that multiple times in practice, and there is even one helper function that will improve the speed of this operation significantly, that we will discuss later. But this is still a drawback. The other drawback of a dictionary is actually coming from its main advantage. It is the fact that dictionary values might be located very sparsely in memory. And this means that the accesses to the otherwise sequential elements in the dictionary, for example, if you are going to iterate these keys, they are not guaranteed to be present in the same memory area. And for modern processors, that means a big performance hit because they will not be able to predict which memory area you are going to address next. And this is called cache miss, and it is usually a big performance hit for any program that has this kind of behavior. On the other hand, if you are not going to iterate dictionaries sequentially, then you are good to go. Okay, now that we know what are lists and dictionaries, let's talk about mutability and copying. This is one thing that you need to understand very, very carefully when you are working with lists and dictionaries especially. Both these data types, when you are creating them, the variables that hold these values, they are not actual variables. They are references to the memory location of those objects. Let me give you an example. Let's say we have two variables, a equals 50 and b equals 70, and then we have a list that contains values from these two variables sequentially. And let's output it. So we have list C, which has values 50 and 70 in it. Now let's make an assignment. Let's say that C2 equals C. And C2 will also print out 50 and 70, as we would expect in mathematics. The problem, however, comes if we will try to modify either of these. So if we will say that C2 element 1 will be now equal to, or element 0 will be now equal to 51 instead of 50, and we display C2 now, we'll have 5170, which is expected. But if we displayed C, we will also get 5170, which is not expected because we never modified C. And this is because both C and C2 are not actual values, but references that point towards the same data structure that is represented by this line. So when we first executed this line, we created a memory structure in memory and assigned C with a reference to that memory. And whenever we did this assignment, we just copied that reference from C to C2 without making any actual duplication of the memory. And the same problem appears in dictionaries. So if you will have a dictionary and then you will make assignment of that name to another dictionary and then you will modify original one, then you will get modifications in both dictionaries visible at the same time. In Python terminology, this is called passing variable by reference. This is in contrast to, for example, normal variables, a, b, or strings that are passed by value. And for those variables that are passed by value, the normal logic applies. So if we have a equals to 50 and a2 equals to a, and then a2 equals to 51, a will still be 50. But if we had the same sequence but as a list, so we would have had a list with just one element, 50, and we would have assigned that list in whole, and then we would have assigned the 0 element. As you can see, that would result in modification. On the other hand, and this is one benefit of this approach, because dictionaries and lists are actually in many cases very large structures, when you transfer these dictionaries and lists into the functions so that you can compute something, you don't actually make any copies and avoid using computational resources for that. However, in cases where you actually need to make a copy because of your algorithm or because of the way you planned your program. You need to do that manually. And to do that, in Python, we are using copy module. And that copy module has two functions. One function helps us to copy simple dictionaries and simple lists. It's called copy.copy. Now C3 is a perfect copy of C, which is still an independent structure. So if we'll have C3 and C, initially they have the same values. But now if we will modify C3 element 1 to be 71, C3 is modified as expected, but C is not. And this is also expected because we have forced Python to actually make a copy of that referenced value. So C3 doesn't point anymore to the same structure as C originally did. However, if we were to take this one step deeper, and if we were to make a list of lists, this is essentially a 2x2 matrix. And as you can see, we have now this element. And let's make a copy of that. So we copy it to C3. And let's do the assignments. Let's assign 0, 0 to some new value like 15, for example. And let's see what will happen here. So this value has been changed. But now the same value also has been changed here, even though we have made a copy. So what's the problem here? The copy is algorithm for what's called shallow copy. The shallow copy means that it only copied first level of references. So it opened our list C, and it went through the elements there, and it copied the value of this block, and then it copied the value of this block. But the problem is this value is also a reference, and this value is also a reference. So when we have made this kind of assignment, we actually followed this reference to the same memory block that was originally pointed by C. Now this might be a little bit difficult to grasp immediately, but the logic is very simple actually. So if you have a list or a dictionary, and you have just one layer of reference, just one variable directly, and then inside everything is passed by value, then it's enough to have a shallow copy like this. Otherwise, you will have to make what is called deep copy. The deep copy will go through every element of C, and it will actually copy all the references with deep copy as well. So if it will go through a list and it will find a reference to another list, then it will iterate through that list recursively until it will copy everything that is going in that tree. So we have now C3, and let's try assignment again. As you can see, now C3 changed and C stayed the same. So with deep copy, we are guaranteeing more or less that our structure will be completely unique, and it will have completely new set of memory, even if there are built-in references and even deeper references than 2 levels. However, this algorithm is very costly, and making such copies might take significant amount of time if you do it in large amounts.